Hi, this is the exercise we were working on last time we were in class. I asked you to imagine a small population of 5 people. Just it could just be any 5 people who have something in common with each other, such as a family of 5 people, maybe. And we sorted out this population into all possible samples of 2 people, meaning all possible pairs of 2 people. And I did sort these out in front of the class. The way I did it is I paired 20 with 22, 20 with 24, 20 with 26, and 20 with 28. And that became the first 4 samples. After I was finished with 20, I moved down to 22, and I paired 22 with all numbers under 22, which became 22 and 24, 22 and 26, and 22 and 28. So I paired 20 with all numbers under 20, and then I moved down to 22, and I paired 22 with all numbers under 22. Then I moved down to 24, and I paired 24 with all numbers under 24, which meant the 2 samples were 24, 26, and 24, 28. There were these two right here. And then 26 could only be paired with 28, because 28 is the only number under 26. So that was the last sample right here. I already calculated the mean and the standard deviation for you. The mean was pretty easy to find. We just had to add up the 5 numbers and divide by 5. The standard deviation I found with Excel, but if I wanted to find it by hand, I would just have to subtract each number by the mean of 24 and then get the deviations and the squared deviations. What we did first is we found the middle 8 samples. What I mean is we found the 8 samples in the center. Actually, that was actually my first question, was what what are the 2 boundary points of the middle 8 samples? Let me put that question on here. What 2 sample means are at the boundaries of the middle 80% of the possible samples? It says 80%, but since I gave you 10 samples, 80% just means 8 out of 10. If I give you 10 samples, then 80% means 8 out of 10, 70% means 7 out of 10. So let's actually find the middle 8. They go from here, sample 2, all the way up to sample 9, because there's 1, 2, 3, 4, 5, 6, 7, 8 samples in there. So it looks like the 2 means that are at the boundaries of the middle 80% are 22 and 26. Now if I had said 70% of the possible samples, well, 70% actually wouldn't work. 60% would work, because 60% of 10 is 6 out of 10. So you would just find the middle 6. And that would be 1, 2, 3, 4, 5, 6. The boundaries would be at these 2 points if I asked you for the middle 60%, because 1, 2, 3, 4, 5, 6 samples are in there. But I asked you for the middle 80%, which meant 8 out of 10. The two answers are just 22 and 26. What if I asked you, what is the 80% margin of error? Before we can find the 80% margin of error, we have to know what the boundaries are of the middle 80%. And we know that they're 22 and 26. What you can do now is take the population mean, which came out to 24, and find how far away that population mean of 24 is from these two boundaries. So the 80% margin of error is just the distance from the population mean to the two boundary points of the middle 80%. This is our population mean of 24. Sample 6 has a mean equal to the population mean of 24. So this is where the population mean of 24 is. If you want to find the margin of error, you could take the population mean of 24 and subtract it by the lower boundary of the middle 80%. So the population mean minus the mean of the lowest sample at the lower boundary of the middle 80% gives you the 80% margin of error. Let's do that. Let's subtract the population mean of 24 by the lower boundary of 22. (24 minus 22 equals 2). It looks like 2 actually is the margin of error. All this 2 really means is that the distance from 24 to 22 is 2. It's just the distance from the population mean at the center to the lower boundary of the middle 80%. It's also the distance from the population mean of 24 to the upper boundary, which was at 26. And the reason why this is called the 80% margin of error is basically just because these two boundaries mark off the middle 80%. If these two boundaries marked off the middle 60%, this distance here and this distance here would be called the 60% margin of error. So our answer is 2. Okay. If we take we can create something called a confidence interval. I'll explain what that means. Take the mean of one of the possible samples and create a confidence interval around it. All we have to do is take one of these samples, take its mean, which is a sample mean, and add and subtract the margin of error to the mean of the sample. I decided to work with sample 3. 23 plus or minus 2. 23 plus 2 is 25. And 23 minus 2 is 21. 21 to 25. Our confidence interval is 21 to 25. Confidence interval is really just the range, meaning the interval between those two numbers. Goes from 21 to 25. And notice how when we created our confidence interval, we took the mean of sample 3 and we added and subtracted the 80% margin of error, which we found out was 2. If we're adding and subtracting the 80% margin of error, the confidence interval is called an 80% confidence interval. So I could say right here, the 80% confidence interval goes from 21 to 25. The reason why it's called an 80% confidence interval is just because we used the 80% margin of error. I'll write this confidence interval under here because it's a confidence interval that was created with sample 3. What if we did it with sample 1, which is outside of the middle 80%? If we made it an 80% confidence interval, it would go from 19 to 23, because we're taking 21 and adding and subtracting 2. If we take sample 10, which is above the middle 80%, and we add and subtract 2 from 27, we get a confidence interval of 25 to 27. Notice how the confidence interval that we created with sample 1 didn't include the population mean of 24, and the confidence interval we created with the highest sample also didn't include the population mean of 24, but the sample that we used in the middle 80% gave us a confidence interval right here that did include 24. So if you want to create an 80% confidence interval by adding and subtracting the 80% margin of error, it'll only include the population mean if you use one of the center 80%, one from the center area, and it won't include the population mean if you use a sample outside of the middle 80%. So think of it this way. You add and subtract the 80% margin of error, you get an 80% confidence interval, and that confidence interval will only include the population mean if the sample came from the middle 80%. Okay. What if, way back at question 1, I didn't say the middle 80%, but I said, what two samples are at the boundaries of the middle 60% of the possible samples? Well, since we have 10 numbers, the middle 60% is just the middle 6. That goes from the lowest one is sample 3, the highest one is sample 8, because there's 1, 2, 3, 4, 5, 6 in the middle. The way I think about it is, if there's 6 inside of here, there's 4 that aren't inside of there, which would mean 2 below down here and 2 above up here, and then 6 would be in the middle, and this would be the middle 6. Okay, so the boundaries of the middle 60%, meaning the middle 6, are 23 and 25. How far is this lower boundary right here of the middle 6 of the samples from the population mean of 24? Well, we could do the same thing again. We could take 24 and subtract 23. We could take the population mean and subtract it by the lower boundary, and 24 minus 23 is 1. So if I asked you, what are the boundaries of the middle 60%, you would say 23 and 25. And if I asked you, what's the 60% margin of error, you would say 1. The 60% margin of error is just the distance from the population mean to each of the two boundaries of the middle 60%. So now you know how to do the problem if I said 60% instead of 80%. What if I said take one of the possible samples and create a confidence interval around it? We could take one of these samples and add and subtract the 60% margin of error to create a confidence interval. For example, right here we could add and subtract 1, and we would get a confidence interval of 22 to 24. We just take the sample mean, add and subtract the margin of error. Notice how we're adding and subtracting the 60% margin of error. Since we're doing that, it becomes something called the 60% confidence interval. So the 60% confidence interval goes from 22 to 24. We're doing 23 plus or minus 1. And this is the 60% margin of error. You can try doing this yourself. You can try taking one of the samples that are below the middle 60% and using it to create a confidence interval. You can take one of the samples from the middle 60% like I did and create the confidence interval, and take one of the two that are above the middle 60% and create a confidence interval. And you'll notice that only the ones in the middle 60% include the population mean of 24. Let's look at an example. What if I used 22 right here, which is below the middle 60%? The 60% confidence interval goes from 21 to 23 when I'm adding and subtracting the 60% margin of error. It doesn't include the population mean of 24. We already did this with sample 5, which is in the middle 60% in the blue area. What if we do it with 26 that's out here above this blue area, above the middle 60%? We get, if we add and subtract 1, we get 25 to 27. So these are all 60% confidence intervals because they were all created by adding and subtracting the 60% margin of error of 1. When we did it with a sample below the middle 60%, right here, the 60% confidence interval did not include the population mean. This 60% confidence interval did include the population mean. This 60% confidence interval up here did not include the population mean. So if you're creating an 80% confidence interval, you have to choose a sample from the middle 80% for the confidence interval to go across the population mean. If you're creating a 60% confidence interval, you have to select one of the middle 60% to make the confidence interval go across the population mean. Also notice how the 80% confidence intervals are always wider than the 60% confidence intervals, because when we were adding and subtracting 2 to create the 80% confidence intervals, we ended up with confidence intervals that had a span of 4 numbers. Like this became 19 to 23 by adding and subtracting 2. That's a span of 4 numbers. When you take a sample mean and add and subtract 1, like we did here, you get a confidence interval that only has a span of 2 numbers, like 21 to 23, which is narrower. So when you add and subtract a smaller margin of error, you get a narrower confidence interval. Now let's see if we can use a z-score to actually give us a formula that can actually give us the margin of error that we already found. Let's see if we can use a z-score to get this margin of error of 2. In order to do that, we have to look at this sample at the upper boundary of the middle 80%, which was sample 9. And we have to create a z-score for sample 9 at the upper boundary. Well, a z-score for a sample is just the sample mean of 26 minus the population mean of 24. You have sample mean minus population mean on top. You have population standard deviation on the bottom. Over the square root of the sample size. All of these samples have a sample size of 2 because they're 2 numbers. So the square root of the sample size goes right here. If you take this, well, first let's find out what the z-score actually is. The square root of 2 is 1.41. If I divide 2.83 by 1.41, I get 2. Looks like I'm getting 2 on the bottom. Okay. I'm not quite sure if that's correct, but we'll see if it is. The top is 26 minus 24, which is 2. This comes out to 1. I'm going to double check my work on the bottom again. Looks like it does come out to 1. What we can do now is we can take this value and it becomes something called our confidence coefficient. The z-score at the upper boundary of the middle 80% of the samples is called the 80% confidence coefficient. I'll just put 80% CC. This z-score of 1 is our 80% confidence coefficient. How can we take the confidence coefficient and get the margin of error? It turns out that you can get the 80% margin of error by multiplying the 80% confidence coefficient by the bottom of the z-score that was actually used to calculate this formula. I mean, you can take the bottom of the z-score and multiply it by the confidence coefficient, and you actually get the margin of error. I'm going to try to explain why this is the case. Notice how when you subtract on top, you get 2. So actually, the top of the formula up here gives us our margin of error of 2. The margin of error is just 26 at the upper boundary minus the population mean of 24. So that is the 80% margin of error. But if we take our confidence coefficient and multiply it by the bottom of the z-score, which was the population standard deviation over the square root of the sample size of 2, this will have to come out to 2. Here's the work that we just did to get our 80% margin of error, which we already know equals 2. We found out that it equals 2 way back at the beginning, but we discovered a formula that would give us the margin of error. We multiply the 80% confidence coefficient, which is the z-score at the upper boundary of the middle 80%, by the population standard deviation, which is over here, over the square root of the sample size, which is 2 because all of these samples have 2 people. We get our answer for the 80% margin of error. We could look at this in a graph to just help us get a little bit more of a sense of how it would look visually. What I'm going to do is I'm just going to make stack some boxes, and each box is going to be a possible sample. our possible samples go from 21 up to 27. So this number line will have to go from 21 to 27. Looks like we have one sample with a mean of 21. That'll be one box. We have one sample with a mean of 22. We have two samples with a mean of 23. We have two samples with a mean of 24. So that's two boxes. 25 is also two. And then we have 126 and 127. The middle 80% is the eight samples in the middle, because 8 out of 10 is 80%. And we said that the middle 80% goes from 22 right here up to 26 up here. The mean of one of the samples, or the mean of two of the samples is 24, because the mean of sample 4 is 24, and the mean of sample 6 is 24. The 24 is actually the population mean. So we'll label the population mean right here. These just happen to be two samples that have a mean equal to the population mean. The sample is at the boundary of the 80%. It's at the upper boundary of the 80%. The sample is at the lower boundary of the 80%. The distance from the population mean to these two samples is the 80% margin of error, which is 2. And right here, the sample at the upper boundary had a z-score that came out to 1, which means that we could label the z-score of this sample right here z equals 1. All that means is that this box has a z-score of 1, because sample 9 has a z-score of 1. We calculated that. And we know that this is our 80% confidence coefficient at the upper boundary of the middle 80%. This is just a way to look at it visually. Now, what if we wanted to use the same formula to try to calculate our 60% margin of error, which came out to 1? We could do that. Once again, the first step is going to be calculating the confidence coefficient. If we want the 60% margin of error, we don't get the same confidence coefficient that we did before. This time we'll have to get the z-score at the upper boundary of the middle 60% up here. Because if you want the margin of error to come out to 1, you have to get the z-score at the end, or at the upper end of this margin of error. So let's get the 60% confidence coefficient, which will be the z-score at the upper boundary of the middle 60%. How can we do that? well, instead of being the z-score of sample 9, it'll be the z-score of sample 8, because sample 8 is at the upper end of the middle 6. The middle 6, which are 3, 4, 5, 6, 7, and 8, are the middle 60%, because 6 out of 10 is 60%. So sample 8 is at the upper boundary of the middle 60%. This time we just take the mean of sample 8, which is 25. We subtract that by the population mean of 24. On the bottom we'll have the same values that we had down here, because when you find the z-score of a sample, you always have the population standard deviation and the square root of the sample size on the bottom. So notice how the only thing that's changed is that instead of using the mean of sample 9, which is 26, we're using the mean of sample 8, which is 25. This is the only number that's changed. And the fact that we're no longer using the mean at this boundary point, and we're now using the mean at this boundary point, is what changes this z-score to a 60% confidence coefficient. I could label this as 60% confidence coefficient. The percentage is just comes from whatever boundary point it's at. If it's at the upper boundary of the 80%, it's an 80% confidence coefficient. If it's at the upper boundary of the middle 60%, it's a 60% confidence coefficient. What if we take this formula and just replace the 80% confidence coefficient with the 60% confidence coefficient right here? If you calculate this z-score, they'll come out to 0.5. So the 60% confidence coefficient comes out to 0.5 in this case. This part of the formula doesn't change. It's still the population standard deviation over the square root of n. The fact that we've replaced the 80% confidence coefficient with a 60% confidence coefficient will make the margin of error come out to the other margin of error, which is 1, which we had way back when we found out that this equals 1. And I said that 1 is a 60% margin of error because it's the distance from the population mean to the lower and upper boundaries of the middle 60% of these samples. the new confidence coefficient makes it come out to the 60% margin of error. So it's really the confidence coefficient that we plug in that determines what margin of error we get. We have a formula now where we can actually calculate the margin of error that we want to calculate. So it's another way of getting these same numbers other than just finding the distance from the population mean to the boundary points like we did at the beginning of the video. Let's take a look at this graph one more time. I can maybe even make it bigger. Let's see. This was the graph of the possible samples. This was our population mean of 24. The distance from 24 to the boundary points of the middle 80% of the samples was 2. That's why that's the 80% margin of error. And the z-score at the upper boundary of the middle 80%, which was this sample here, was a z-score of 1. So this was called the 80% confidence coefficient. The distance from the population mean to the boundary points of the middle 60% is our 60% margin of error. These two samples here, meaning these two numbers, 23 and 25, marked off the boundaries of the middle 60% because inside of here we have 1, 2, 3, 4, 5, 6 out of the 10 possible samples. And the distance from the population mean of 24 to these boundary points of 25 and 23 was our 60% margin of error, which was 1. And the z-score that went along with this upper boundary of 25 was our 60% confidence coefficient. The z-score at the upper boundary of the middle 60% is the 60% confidence coefficient, and it came out to 0.5 when we calculated it before. And I told you that if we take this z-score of 1 and we plug it into that formula I showed you earlier with the population standard deviation and the square root of the sample size, we get this margin of error of 2. If we plug in this confidence coefficient of 0.5 into that same formula, we get our margin of error of 1. So what if we had a situation in which we didn't actually have a graph of these possible samples and we still wanted to get the margin of error? Well, I'll show you how to do that next. Before we do that, we have to think about the shape that the possible samples are following. It might look a little bit like a normal curve because it well, you have this high point in the middle, and then the shorter points at the two at the two tails. But it isn't really a nice normal curve because it's too flattened out. It doesn't really peak like a bell curve would. But if you were drawing from a set of possible samples that actually did follow a bell curve, like this, if the boxes actually did follow a normal distribution, then it turns out that the confidence coefficient can actually be looked up in a table. For example, if the possible samples follow a normal curve like this, then the upper boundary of the middle 95%, well, I'm not going to use 95% because I want to stick with what we were doing already. We were doing 80%. It turns out that you could actually look up the z-score in a table at the upper boundary of the middle 80% of your samples. If the possible samples, meaning that all of the boxes that you're drawing from, follow a normal curve, the z-score at the upper boundary of the middle 80% will always be roughly 1.28. And I actually found that out by looking at a normal curve table. And let's compare that with what the z-score was at the upper boundary of the middle 80% in this set of samples. It came out to 1 when we calculated it. And what this says is if these samples followed a normal curve, the z-score at the upper boundary would be 1.28. Our set of samples isn't that far from being a normal shape, which is why it makes sense that our z-score of 1 came out close to what the table gave us, which is 1.28, because the closer our set of samples is to a normal curve, the closer this z-score will be to what the table gives us, because what the table is giving us is what this z-score equals when the possible samples perfectly follow a normal curve. And I'll actually show you how I got this from the table. What I had to do was I had to go inside this table, the normal curve table, and actually find the closest decimal. And what I actually had to do first was I had to find the total percentage, not just in the middle area, but all the way to the left. And I'll explain why. The way the z-table is set up is to give you areas to the left of the z-score, meaning from the area from the z-score all the way to the left of the curve. And if the middle area is 80%, then the two tails have to be 10% and 10%. if you want to find the tails, what you do is you subtract 100% by 80%, and you get 20%. And 20% is everything outside of the center area, meaning the total of the two tails is 20%. And then if you divide 20% by 2, you split the 20% in half, and you get your two tails at 10% and 10%. And then to check your answer, you have to make sure that all of these tails add up to 100%. And these three numbers do add up to 100%. Now the total area to the left of the z-score is the center 80% plus 10% in the tail, which would be 90% of the samples. If I change that to a decimal, it becomes 0.90 if I move the decimal point. What I did was I went inside the middle of the table and I found the closest decimal to 0.9 for 90%. And it actually, the closest one was 0.8. I believe it was 0.877. No, I believe it was 0.8997. That's very close to 0.9. And what I had to do is I had to go to the row over here and the column up here. Over here I got 1.2. And for the column I got 0.8. Sorry, this should have actually been 0.08. If you piece the rows and columns together, all you do is you put the 8 after the 1.2, and when you put the 8 at the end, you get 1.28. And then that's the closest, the z-score that's the closest to this point that we were interested in up here, with 90% of the curve to the left of it. That's how I got the 1.28. So the important point is that if you know that the samples that you're drawing from, which are these boxes, follow a normal curve, then the confidence coefficient at this boundary can just be looked up in a table. Because it's, if the samples follow a normal curve, this is always the confidence coefficient at this boundary point. Now how can we predict if the samples will follow a normal curve? Because they didn't quite follow a normal curve in this case. If you take a sample from a population that follows a normal curve, meaning if the individual people in the population follow a normal curve, then the samples also follow a normal curve. That pretty much means if these numbers here follow a normal curve, then these numbers here also follow a normal curve. If the population is normal, then the samples are normal. Also, if you take a sample of at least 30 people from a large population, then the samples are always normal. The boxes that you're drawing from would always be normal in that case. So let's take a look at an example. I recruit a sample of 40 SJSU students and record their heights. I calculate the mean height of the sample by adding up their answers and dividing by 40, and it turns out to be, let's say, 62 inches. What if I asked you to calculate the 80% margin of error and to also calculate an 80% confidence interval? If the sample size is 30 or higher, then the samples that we're drawing from at least roughly follow a normal curve, like they do here. Maybe not perfectly, but at least roughly. The guideline is if your sample size is 30 or higher, the samples that you're drawing from at least roughly follow a normal curve, which means that the confidence coefficient would just be this confidence coefficient here, which came from the normal curve table. This would be the z-score at the upper boundary of the middle 80% that we're drawing from. And if we wanted to get the 80% margin of error, we could just multiply the 80% confidence coefficient by the population standard deviation over the square root of sample size. Remember, we discovered that this formula gives you the margin of error that you're looking for. So we would plug in the 1.28 for our 80% confidence coefficient. We would multiply that by the population standard deviation over the square root of sample size. The problem is, how do we know what the population standard deviation equals? How do we know what the standard deviation of the heights of all SJSU students equals? Well, since this is just a made-up problem, we could hypothetically say that somehow we know what it equals. What if I told you the population standard deviation equals 2.8? Now we have something we can work with because we plug in the population standard deviation. We put it over the square root of the sample size. What's our sample size? We're not taking a sample of 2 people from the population. We're taking a sample of 40 people from the population. The square root of 40 is 6.32. And we can now divide this by this. .8 divided by 6.32. equals 0.44. 1.28 times 0.44 equals 0.56. So it looks like the margin of error, the 80% margin of error is 0.56. Let's find out what that actually means. The population mean is somewhere at the center of the possible samples. In this case, the population mean would be the mean height of all SJSU students in the university population. The distance from that population mean to the boundaries of the 80%, to the boundaries of the middle 80% of the possible samples that we're drawing from, is a distance of 0.56. So that is our 80% margin of error. Don't worry about this 90% down here because I know it might be a little bit distracting. It's just what we were using earlier when we found the total area to the left. Now what if we wanted an 80% confidence interval? We take our sample mean of 2.8 and we just add and subtract the margin of error, because that's what gives you a confidence interval. After adding and subtracting, we would have two numbers and we would say the 80% confidence interval goes from this number to this number. And the confidence interval would include the population mean as long as our sample that we selected with the mean of 2.8 with the mean of 62 is one of the middle 80%. So I think I actually did this wrong because I said it was the sample mean plus or minus the margin of error. So the sample mean was actually 62, not 2.8, which would mean that the confidence interval goes from 61.44 to 62.56. And as long as we selected one of the middle 80% and we didn't get a sample from one of the tails, then our 80% confidence interval does cross over the population mean, meaning the mean of all San Jose State students. In order for us to calculate this confidence interval with this formula down here, you could see that we had to have the population standard deviation. This formula was for the 80% margin of error. And once we got the 80% margin of error, we added and subtracted the answer to the sample mean to get the confidence interval. But in order for us to do any of this, we had to have the population standard deviation. In a real life situation, when you're studying a population, you don't have that number, but you have something called the sample standard deviation, which can be calculated. So what if I change this type of question, and instead of giving you a population standard deviation, I say that the sample standard deviation equals 2.8. What would we do now? Well, now what it's going to be is what we can do is we can take out the population standard deviation from the formula and substitute it with the sample standard deviation. So in this type of question, we have a new formula. It's the 80% confidence coefficient times the sample standard deviation over the square root of the sample size. Hopefully I put the square root sign around the sample size last time, because it is, regardless of whether we were using the formula we did before or this one, this is supposed to be the square root of the sample size. So now we need our 80% confidence coefficient. Last time we used 1.28 from the z-table, and it turns out that if we're using a sample standard deviation in our formula for the margin of error instead of the population standard deviation, the confidence coefficient actually won't be the same. And it's actually going to be something called a t-score, and I won't get into too much of the details of the formula for a t-score, but let's just think of that as just an estimated version of the confidence coefficient. So an estimated version of this z-score, which won't be exactly 1.28, but it'll be somewhere close to 1.28. We can get that estimated confidence coefficient by going to a t-table. So if I give you a sample standard deviation instead of a population standard deviation, the confidence coefficient comes from a t-table instead of a z-table. And the t-table is pretty easy to use. What we do is we just go down here, we go to 80%, which is the percentage I gave you for this question. That's going to be our column. We go up to the row that matches up with our sample size. I said we're recruiting a sample of 40 people. Technically, we're supposed to be going to the row that's one less than our sample size, because in a t-table, they actually set it up where each of these rows is not the sample size, but the sample size minus 1, which would mean instead of going to 40, we should be going to 39. But they don't have a 39, so let's just go to 40 instead, because that's the closest. We get 1.303, where the row and column meet up. So our confidence coefficient is actually 1.303. So since we're using the sample standard deviation instead of the population standard deviation, we had to use the t-table instead of the z-table to get the confidence coefficient. And I said it was an estimated confidence coefficient, so it's a little bit higher than what we had before. Let's take our sample standard deviation here, divide it by the square root of our sample size, which is still 40. If we complete this formula, we're going to get the 80% margin of error, because this is the margin of error formula that we're using. And once that comes out to a number, the 80% confidence, to get the 80% confidence interval, just take your answer and add and subtract it from the sample mean. So to get the confidence interval, just take 62 and then add and subtract whatever answer you got for the margin of error. And remember, the margin of error comes from this formula right here. This is how a confidence interval would be calculated in a real-life situation. You would use the sample standard deviation because that's usually all that's available to you.